Hey guys, welcome back. We're going to go over the study guide. It's going to be uh, the test on sound and waves for regular physics 11th graders, and it's going to be the final for 12th graders. A couple of the questions on here have to do with light, and we're going to skip those. We didn't get as far. I didn't realize they were going to jam pack so many things in the last couple of weeks. So I apologize for that, but I'll try to be clear on what we're not covering. All right, so they want us to identify what these letters are. Looking at this first one, A goes from an area of compression to an identical area of compression. So this, for me, would be a measure of wavelength. C would be a point of compression, and B would be a point of rarefaction, which is what they call when that's spread out, the rarefaction. On the one down here, A is again a wavelength. C is pointing to these 0 points. Those would be nodes. D is pointing to peaks and troughs. Those would be antinodes. And B in this one is pointing to how high this is. And this would be a measure of the amplitude. So that's going to be the amplitude of our wave. So that's going to be related to our energy and how much we initially displace it. Suppose that two sound waves passing through the same medium have different wavelengths. Which of the following is most likely to be the reason for differing wavelengths? Frequency would be why they have different wavelengths. So frequency is inversely related to wavelength. Different amplitudes can absolutely have the same wavelength. Superposition of mechanical waves can be absorbed in the movement of. So this is when waves overlap each other, cancel each other out, or add each other together. So we saw this in our diffraction lab, right? Where we had waves overlapping with each other. And they used water waves to show this. When two mechanical waves coincide, the amplitude of the resultant wave is always.
Chris Ledge, if you are in the building, please report to the main office. Chris Ledge to the main office.
And this is going to be the sum of. So we're going to arithmetically add it. If it's below the line, we're going to take that as a negative amplitude that we add to the other positive amplitude above. Two mechanical waves that have positive displacements from the equilibrium position meet and coincide. This would be constructive interference. So constructive interference is going to be waves adding together. Number 7, two mechanical waves meet and coincide. One has a positive displacement from the equilibrium. The other has a negative displacement. This is going to be deconstructive. So they'll be canceling each other out. And we'll see a couple more examples of those. All right, number 8, when these two meet, this one is going to have an amplitude of positive A. This is going to have an amplitude of negative A. It looks like they're equal and opposite amplitudes, so this would be destructive. So it looks like it would be complete destructive interference. Waves arriving at a fixed boundary are reflected and inverted. If you remember when I was doing the demonstration with the spring, the brick wall was our fixed boundary. If it's a free boundary, they are reflected but not inverted, which was, like I said, that's hard to demonstrate. But in the FET, which was wave interference, you could see that if you put it to the end and it had the little ring and went up, it would bounce back the same way. Standing waves are produced by periodic waves of, they need to have any amplitude, but they're traveling in opposite directions. So when I was doing the ones with the spring, we were sending them down and they were bouncing back. The wavelengths are matching up, so it's constructive, and it was getting bigger and bigger. All right, 12. How many nodes? How many antinodes? Nodes are zeros. So that's where we have no energy. And I showed you this in the microwave diagram. I showed you this when I did the spring up and down. So we would have nodes. Antinodes are peaks, whether it's above or below. That's where we have the most energy. And it looks like we have 4 of those. So we have 5 nodes and 4 antinodes. Sound waves are longitudinal waves that are mechanical waves. So they're not electromagnetic waves, and they do require a medium. The highness or lowness of a sound is what we think of as a pitch. And a high pitch is going to be a high frequency. In general, sound is going to travel faster through. So sound goes from particle to particle to particle to particle. So the closer the particles are together, the faster that it's going to go. So it's going to go faster through solids than gases. And this is in general because this isn't always the case. There's examples of rubber where it actually slows it down. The Doppler effect is going to work for all waves. So this relative shift in frequency, whether you're moving towards something or moving away from something. If you're on a train, how will the pitch of the train's whistle sound to you as the train moves? It should be constant. So you shouldn't be able to notice it because you're moving along with the thing that's generating the sound. The difference is only going to happen if it's moving towards you or moving away from you. The perceived loudness of a sound is measured in decibels. Audible beats are formed by interference of waves that are slightly different. And I did this in an example up front. We did 125 and 128, and we did 256 and 259.6 or 59.7. And however many wah, 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 wahs you hear per second is going to be how many beats you have. So in the case of the 128 and the 125, we had 3 beats per second. The numbering goes weird. It skips up to 26. You don't need to worry about 26. We might get to a little bit of light next week, but I needed to have an endpoint where we could get to a study guide and get it ahead of time before you guys took the final. If you know the wavelength of any form of electromagnetic radiation, you can determine its frequency because the speed is going to be this 3 times 10 to the 8 meters per second. And we did cover this, right? So this is going to be a constant in a vacuum. 29 and 30, you don't need to know, but we'll get to those for the final for the juniors in here. And the same with 31, 32, and 33. So that's nice that we don't have to worry about those. And the same with 34. All right, so what kind of wave is this? If my disturbance is vertical and my wave travels perpendicular, we call this a transverse wave. Two, you don't need to worry about, but this is all electromagnetic radiation. So this is going to be microwaves, gamma rays, radio waves, visible light, ultraviolet, infrared. All of those are all going to travel at the same speed. Waves that need a medium to travel through are mechanical waves. And this type is a longitudinal wave. So a longitudinal wave, where this one, our displacement and velocity are perpendicular, and this one, our displacement and velocity are parallel. All right, the wave is going to travel faster in a lighter one would be a looser medium, right? So if they have the same tension, it's going to be easier to move molecule to molecule in light ones. All right, so here we have our loose end and our fixed end. So what we saw is as the pulse got to here with the loose end, this went up, and then our pulse stayed above it and bounces back in that way. In this one, this is like the brick wall example, and when it gets to here, it's going to flip down and travel back along the bottom. All right, what's it going to look like when these meet? Well, we're going to have constructive interference. So it tells me that this one has an amplitude of 4, this one has an amplitude of 4. These are both up. So together, when they meet, they're going to get an amplitude of 8. So you would just arithmetically add the amplitudes. Now here, this one says 2, but it really means negative 2 because it's below. So what's it going to look like? Well, I'm going to have one that has an amplitude of 4 because 6 minus 2 is 4. Number 9, we're going from a high medium to a low medium. So what's going to happen is that some of it is going to bounce back and some of it is going to continue on. All right, now these two have to do with the wave speed worksheet, which we're going to do after we do the study guide, but it's the only equation that we need for this section. And so generally, this is going to be the frequency times the wavelength. The way this changes for light is that in this case, this is a constant value. So if I want to get the wavelength, I'm just dividing this speed divided by the frequency. So I have 3 times 10 to the 8th meters per second divided by 950 million hertz, which tells me how many times this happens every second. So 1, 2, 3, 4, 5, 6, 7, 8. So I have 0.315 meters. All right, so down here, we have a car beeping. The velocity is not going to be the speed of light. It's going to be the speed of sound. And they should tell you, but it's either going to be 330 or 343 are typically the two that we use in problems like this. So again, our velocity is frequency times wavelength. So to get the wavelength, I'm going to take the velocity over the frequency. So if I use 330, I'm going to have 330 divided by 1250. So it ends up being 0.264 meters. All right. So the other part of this where you're going to have to do math is with wave speed problems. So I wanted to go over this in the same setting as that. We did a couple of these in the notes, and we did it both as an example in the notes, but also that's how we determine the speed of light using the chocolate bar, right? We use this equation specifically for light. So a wave with a frequency of 14 hertz. So hertz is second inverse, which just means 1 over second. So how many times is this happening per second? All right, so velocity equals frequency times wavelength. So we have 14 times 3, which is 42. All right, so in this one, they give us the speed, and now they want us to get the frequency. So the frequency is going to be the velocity divided by the wavelength. And so this is going to be 65 meters per second divided by 0.8, which is 81.25 hertz. There's not a lot of equations in this. There really isn't. When this was an AP subject, when it's on the AP test, there was only one equation listed. And there was a couple other they had to memorize or be able to derive, but there's not a lot of equations in sound. All right, again, we have a frequency of 46 hertz and a wavelength of 1.7. I want to get the speed. So this is going to be velocity equals frequency times wavelength. So this is just going to be 46 times 1.7. That startled me. A wave traveling at 230 meters per second has a wavelength of 2.1 meters. What's its frequency? Again, the same formula. Now we're getting F by itself. So I'm going to divide both sides by lambda. And it looks like that says 109.5, but I'm going to check that because that could be a 4. I can't read the... Yeah, it's 109.5. All right, and then just a couple more. A wave with a frequency of 500 hertz is traveling at 200 meters per second. What's the wavelength? Again, same formula. And this is on our final as well. We'll have a study guide for the end of the year final. And everyone in the district uses the same final. So we have a study guide that goes through all of that. All right, I'm going to do the same thing. Velocity equals frequency times wavelength. I'm going to solve for the wavelength. This is going to be velocity over frequency. So this makes me think that this is a sound because it's 340, which is between 330 and 343 that I told you just a little bit ago. So that seems like a reasonable one. This is 0.63 meters. A wave is a wavelength of 125 meters and it's moving at 20. What is its frequency? So I'm going to multiply by 1 over lambda or divide by lambda. This ends up being 0.16 hertz. A wave has a frequency of 900 hertz and a wavelength of 200. What's its speed? In this case, you don't even have to move the equation around. It's in the proper form for you. So this is going to be 900 times 200, which is 1.8 times 10 to the 5th meters per second. And then a wave has a wavelength of 0.5 meters and a frequency of 120. So we have 120 times 0.5, which is 60. And then the final one, and this is going to be the only thing about light that you're going to be responsible for, is this equation, because there are some that are at the speed of light, which is really easy because it's a constant. So you always know what that is as long as it's going through a vacuum. So radio waves are going to travel at 3 times 10 to the 8th meters per second. WFNX, broadcast radio waves at a frequency of 101,700,000 hertz. So if you looked on a radio dial, it would say whether it's kilohertz or megahertz. And in this case, this is megahertz. That's a million. So this, if you were putting this on your dial, it would just be 101.7. You come in, Bobby.